Okay. When an event has a single outcome, like rolling a six on a die, or flipping a coin and getting heads, we call it a simple event. It's got a single outcome. So that's a pretty simple scenario, and you can learn a lot from that. Um, but you also have something called uh, compound events, where two or more simple events are happening. A very uh, basic one would be uh, flip a coin and roll a die. That's two completely separate events, all right? And we have to consider whether the events can occur at the same time. They like to use uh, cards here for it. So for you have to know some stuff about a standard deck. A standard deck of cards has 52 cards. It has four suits, and they are diamond, heart, um, club. That's a wonderful looking club there. I messed it up. Dang it. Club and spade. Uh, the heart and the diamonds are red, and the club and the spade are black. And you have ace, king, queen, jack, 10 through 2. And those are different cards, and there's 13 cards in each suit. So those are all the stats that you basically need to know. So what we're going to be doing if you're working with a deck of cards, you're looking to see if things are mutually exclusive, which means they cannot occur at the same time. So the examples that they have is you pull a single card from a deck. Is it a queen or is it a king? Well, those two things are mutually exclusive because a king can't be a queen and a queen can't be a king. So you get to pull one card, only one of those two things is happening. There's no overlap at all. For a not mutually exclusive event, um, we're looking for things that can both happen. So we were talking about suits here, the diamonds, hearts, clubs, and spades. The spade has a king. Well, you can pull a king out that is also a spade. So if your option is pull out a king or a spade, well, you'd have this problem here where you might have both things happening at once with the king. So what does this all mean? Usually, we can just go with our normal counting principles, and if they're mutually exclusive events, the counting works just fine. But if they're not mutually exclusive, we have to do something. We have to take out whatever overlaps. Because it's being counted in both circles, if we don't take it out, it's going to be counted twice. Let's take a look here. So we have four things happening here and four things happening here. Well, I would just add those up, add a 52. For the kings, there's four kings, and for the spades, there are 13 spades. But that one in the middle there, the king that is a spade, it was counted in the four kings and in the 13 spades. So I'm going to subtract the one that is both. And then I would divide that by 52. So that's the difference there. If you don't subtract away the stuff that overlaps and then not mutually exclusive, you end up counting it twice and it will throw off your probabilities. Let's go ahead and take a look at some examples. Example 2, we're trying to add probabilities here. So determine whether the events are mutually exclusive or not mutually exclusive. Then find the probability. So, well, one thing, hold on, let me go back up here real quick. I kind of drew these over the big fraction there, but they should actually be calculated out separately and then add it together. So 4 over 52 plus 13 over 52 minus 1 over 52. So that that's how you're supposed to do it. They just all had common denominators, so I just stuck them together in my head. All right, back to the problem. Keisha has a stack of 8 baseball cards, 5 basketball cards, and 6 hockey cards. So there's some 8 baseball, 5 basketball, 6 hockey. If she selects a card at random from this stack, what is the probability that it is a baseball or a hockey card? So we have to decide, is this mutually exclusive or not mutually exclusive? Well, if it's a baseball card, it can't be a hockey card. Those are not the same sport. And the same way, if it's a hockey card, it can't be a baseball card because they're different sports. So here I would say this is mutually exclusive. Now that we know it's mutually exclusive, now we know which one of the two probabilities to use. So the probability of baseball card or hockey card. Well, how many baseball cards are there? There's 8 baseball cards. How many cards total are there? 8 plus 5 plus 6, that's 14, that's 19. Plus, how many hockey cards are there? 6 over 19. Add those two up, you get 14 over 19. So that's the probability there. Part B. Suppose that of 1,400 students, so 1,400 students, that sounds like the total number to me, 550 take Spanish, 700 take biology, and 400 take both Spanish and biology. What is the probability that a student selected at random takes Spanish or biology? So we have to decide, is this mutually exclusive or not mutually exclusive? And this blue bit right here, where it says 400 takes Spanish and biology, we would say that it makes it not mutually exclusive. So we're going to use the probability of Spanish or biology, and that is going to equal the probability of Spanish plus the probability of biology minus the probability of Spanish and biology. So, there are 700 students of the 1,400 taking Spanish. There are, oh no, sorry, that's biology. There are 550 taking Spanish. There are 700 taking biology. And there are 400 that take both. They all have a common denominator. So we have 550 plus 700 minus 400 over 1,400. 550 minus 400 is 150, plus 700 is 850 over 1,400. And you can go ahead and reduce that down. 85 and 140 are both divisible by 5. Let's see, 850 divided by 50, 17. And 1,400 divided by 50 is 28. But 17 is prime, so that's all it's going to be. So I have 17 divided by 28, which is 0.607. Let's just round it to there, approximately. All right. That's all it takes to find some probabilities. And these are just basics in the beginning. It's going to be a lot of just counting everything and trying to figure out whether it's exclusive, mutually exclusive or not. All right, it's all going to be based around that, and then using the correct formulas.